Okay, folks, hello, and welcome to another week of Offsite Learning, our last week. Okay, so to finish off our biology unit, you will need the new notes for June 8th to 11th. They are in the Google Classroom. Again, we did this unit a little more week by week. So the notes for this week will be in this week's agenda, obviously. So they're going to start off on page 27, just because we picked up from where we had left off last time. All right, let's get into this week and finish off Science 20. So picking up with the big ideas for topic 1, look out for these as we go. What is biotic potential? What are J and S curves? What is carrying capacity? What are density dependent and density independent limiting factors? What is an ecosystem's environmental resistance? What is meant by that term? And how does the human population's growth rate compare to other species' growth rates? Okay, so we're now kind of shifting to the second part of our biology unit. We've been looking a lot at ecosystems. Now we're going to start looking more at changes in populations within ecosystems. So how do populations change and evolve over time? Okay, so we'll begin with a definition here. Biotic potential. What is biotic potential? It's just a species' possible rate of growth given unlimited resources and ideal living conditions. So potential, right? It has the potential to grow this quickly if everything is perfect for it. Obviously, that's not very often the case, right? It's just saying if everything were perfect, how fast could this population grow? And so not every species is going to be able to grow as quickly, even if you give it everything it wants, right? Because some factors play a role whether or not it has the resources it needs to reproduce as much as it wants. So here's just some of those factors. So one factor is the number of offspring per reproductive cycle, or in other words, how many babies will it have at once, right? This is one of the reasons that humans have a fairly low biotic potential. We usually have one baby at a time, right? Sometimes two, sometimes three, and then in really rare cases, you can have more than that. But for the most part, we have one baby at a time, right? And so that means even if we have everything we want, we can't grow our population that quickly because we can only have one baby. Compare that to like a dog that can have litters of like 12 puppies. Now, just two adults are producing 12 offspring. Compare that to insects that can literally have thousands and thousands and thousands of babies in just one reproductive cycle. Okay, they can grow their populations a lot quicker if we let them. All right, the number of offspring which survive long enough to reproduce. In other words, how many grow up and then have their own babies. So this is one that where humans are actually pretty good, at least nowadays, right? Most human children will survive to adulthood and usually reproduce, not always. Okay, the number of reproductive cycles per lifetime. So just how many times an adult can give birth. If you can do that a lot in your life, you can have a lot of babies and your population can grow. If you can't, not so much. Minimum and maximum ages of fertility, so when they can start having babies and when they get too old. So if you grow up pretty quick and within a year of being born, you're able to have your own children, well, then your population can grow pretty quickly, right? If you are able to have children for a long time, then you can keep making babies kind of your whole life, right? Humans are not really like this. Humans have to wait a long time till they can have babies, and then they're alive for a long time after they stop being able to produce offspring, right? But again, this is another factor that would let you grow your population quickly if you had everything you needed to. Okay. The length of a reproductive cycle. How long are you pregnant? Humans, again, pretty long, right? It takes 9 months for a human to conceive a baby and then have a baby. There's organisms out there that can do it in like a day. So they can grow their populations a lot quicker if they're allowed to. The time between reproductive cycles. So, again, just after having children, how long must you wait to have more? If you can get pregnant, have kids, and then get pregnant and have kids again a week later, you can grow your population pretty quickly. Okay, and then lifespan, which is just how long they live. This one is not as related to reproduction. It's just the fact that if babies are being born and other organisms, adults, are living for a really long time, well, then your population is growing because older organisms aren't dying off as younger ones are continuing to be born. We would say that the birth rate is higher than the death rate, right? For every one organism dying, you have two new ones being born or something, right? So your population continues to grow. Okay, so growth curves are a way of kind of modeling the way a population grows over time. Now, if a population is allowed to grow with no restrictions, hey, we just learned what that meant. No restrictions on how you're growing. The only thing limiting how you grow is how fast you can make babies and how quickly you're dying, basically. What's that called? You are growing at your biotic potential, right? You're not being limited because there's not enough food or not enough water or whatever. You're not worried about that stuff. All that's limiting how fast you can grow is how fast you can make babies. Okay. We say the growth is exponential. You may have seen that term in math class, right? It means the same thing here. It follows an exponential curve. And we call that, very creatively, a J curve. Why? Well, look at it. It's shaped like a J. Well, without the top part of a J, right? Why would population growth be exponential if you don't have any limits? Well, remember, most organisms are going to have multiple kids. And then all of those multiple kids are going to have multiple kids. And then all of those multiple kids are going to have multiple kids, right? So you're getting more and more and more and more organisms each generation. For example, if you have 3 kids and each of your 3 kids has 3 kids, well, now there's 9 kids, right? And if each of those 9 kids has 3 kids, now there's 27 kids. And each of those 27 kids has 3 kids, now there's 81 kids, right? So it gets bigger and bigger and bigger. Do you think this is sustainable? Do you think this can go on forever? Well, eventually, is there going to be enough food or water or living space to support all of these things? No, right? So some species do grow like this, and then they die off. And a good example is things like bacteria or insects in the summer. They grow like crazy, but then eventually all good things must come to an end and they start to die off, right? They grow a lot while the growing's good, but eventually it can't be supported forever. Now, under most natural conditions, of course, this can't, like we just said, it cannot go on forever, right? There's no way. How do you support that? Eventually, limiting factors, we've seen those before, slow the rate of growth, and it follows an S curve. So your population starts low, you grow, 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 and then resources start to run out, and limiting factors start to limit your population. So you reach kind of a stable point where, okay, this is about the population that can be supported. If we go above it, some of us are going to starve off. If we go below it, we'll have some more babies and bring it back up. Generally, this is where we should be. I just want to note that it's not like it'll just stay flat forever, right? You might get little bumps like this as you go, but it'll kind of hover around this point here, given no disturbances to the ecosystem. So what do you call the area of the graph labeled as K? And what does it mean? So we have seen this before, but now let's really go into it. K is something called the carrying capacity. And it's a good name because it refers to what an ecosystem is capable of carrying, the maximum capacity, right? Elevators have a carrying capacity. They will say maximum 12 persons. That is how many people that elevator is capable of supporting. It's the same idea with carrying capacity in an ecosystem. How many organisms of a species is an ecosystem capable of supporting? What decides that? Well, things like nutrients, water, right? Sunlight, all of those and more decide how many of a certain type of species can live in an area. So just the population that an ecosystem can support. Okay, now carrying capacity, like we've said, is not just some magic number that's always the same. It can change from season to season or from year to year, right? For example, look at Fort McMurray. Like we were talking about during succession, the fires would have changed the carrying capacity for, well, we saw bears, right? There were more bears that were able to be stably supported because the fires took out a lot of the big trees that were hogging all the sunlight and allowed the berries that the bears love to eat to grow in a bit, right? And to come back. It's that secondary succession. So once the carrying capacity is reached, a population remains in what we call stable equilibrium, which just means it'll be roughly around that population. It might go a bit up, might go a bit down, but it'll stay around there, assuming there are no disturbances. If there's a disturbance, there will adjust, and there will be a new carrying capacity that will eventually be reached. Okay, we're going to take a look now at human populations, specifically overgrowth in human populations. So just like in an ecosystem, if human population grows beyond the capacity, problems can occur, right? Things like overcrowding, right? There might not be enough space to live in. Disease outbreaks, very closely related. If everyone is having to pack in very close together, then diseases spread really quickly. We've seen that this year with coronavirus, right? Where was hit hardest by coronavirus? Big cities, places where there was a lot of people packed together. You can get water, food, and housing shortages. This is constantly an issue all over the world, right? There are a lot of places where there's just not enough water or food or homes to provide for everyone, okay? And then, of course, our pollution and waste accumulation. The more people, the more waste we produce, the more pollution we put out, the less the Earth is able to stably support our population. This can lead to the collapse of an entire civilization, just like in an ecosystem, right? If you have exponential growth for too long, eventually the ecosystem will collapse, okay? So just an example, in ancient Rome, okay, Rome was the first city to reach a population of 1 million. Too many people. It couldn't support that many people. There just weren't enough resources. So it grew beyond its ability to sustain itself. The entire civilization ended up crashing to a population of 20,000, and most of the city ended up lying in ruin. Now, this is something that's been studied for a long time. This guy is often given credit for kind of being the first one to really talk about it, although there were others before and after him. So Thomas Malthus was a scientist in the 1700s, and he basically wrote about the dangers of exponential growth. So what kind of curve would that be? A J curve in human populations. And he noted that, yeah, while we were producing more food and water, we weren't producing them as quickly as we were producing new humans. And what's more, eventually they will run out, right? That at a certain point, there'll just be too many people if we continue growing at that rate. So let's now take a look at the history of the human population. For most of its history, the human population has been stable or grown very slowly. So grown a bit, but for the most part, kind of sitting at a stable equilibrium. And then in about the last 200 years, the human population has exploded. I'm going to show you a graph in a sec that shows you what I mean. Okay. Why would that have happened? Why in the last 200 years would the human population have suddenly gone just off the charts? Well, think about what's happened in the last 200 years, right? We've got a lot better, for one thing, medicine now. If you go back a couple hundred years, the common cold that you get 4 or 5 times a year could have been a death sentence, okay? Surviving childbirth was about as common as dying in childbirth. We've had huge advancements in science and medicine. You don't even have to go back that far to find doctors putting leeches on people to try and cure the Black Plague, right? A lot of our medicinal knowledge has come pretty quickly. Not only that, but also agriculture, right? Being able to grow food allows you to feed a lot more people, allows a lot more people to survive and be supported. Okay. Also, industry allows you to transport goods better and make them faster so that you can get them to more people more quickly. So specifically where things really started to take off was in the Industrial Revolution, the mid 1800s, because that's when things started to get industrialized. Living conditions improved, death rates slowed due to advancements in medicine, and birth rates stayed roughly the same. Hey, what did we say? If your birth rate is above your death rate, what's going to happen to your population? Yeah, it's going to grow, right? For every one person that's dying, maybe 2 people are being born. And then those 2 people that are being born are going to each maybe have 2 kids while only 1 person died, right? So now you've got 4 people being born and only 1 person dying. Death rates are going down, birth rates are staying the same. And what's more is the kids that are being born are much more likely to survive to adulthood and have more kids, which is good, of course, don't get me wrong. And now in the 21st century, which is the century we are currently in, this is the first time ever in the world's history that the elderly will outnumber the youth. People are living way longer. It's a good thing for sure. But it does have implications for the human population. So we are not exempt from the rules that govern ecosystems, right? The biosphere, yes, it's all ecosystems, but it's also just one big ecosystem, right, that we are a part of. And so it has a carrying capacity. And that depends on many factors, a lot of the ones we've seen before. So pollution can lower the carrying capacity. If people get too high where we're polluting our resources to the point we can't use them, that's going to lower the number of people that can be supported. Clean water, there is only so much clean water, right? If there's not enough for everyone, there's not enough for everyone. Access to food, access to resources, a lot of these things we might have enough of, but getting it to everybody is an issue, which leads me to distribution of populations, right? It's not like we can just all have a big water store that we all go to. No, we're very spread out. And the infrastructure in a lot of places is very different than in other places. Okay, so just a reminder of the definition of sustainability. What does that mean? If something is very sustainable, it means we're good. We can keep living like this. It's going to work, no problems. Okay? It means you can maintain your current standard of living, keep doing what you're doing without stopping future generations from meeting their needs. So if you can do that, you're living in a sustainable way. If you cannot do that, if living the way you are living now is going to cause future generations is going to have to cause them to use less, otherwise not be able to meet their needs, or to have a lower population, otherwise not be able to meet their needs, then you are living in an unsustainable way. Now, human populations are currently growing in an unsustainable way. The human population is not growing in a way that can be sustained. So the current population of Earth is about 7.7 billion. Many scientists agree that Earth's maximum carrying capacity for humans is about 9 billion. We're almost at 8 billion. It's projected that the Earth's population will reach 10 billion, which is a billion past the carrying capacity, as early as 2050 at the current rate. So if the current rates don't change, then by 2050, we're projected to be a billion beyond the carrying capacity, which means we may not get there. Resources may limit that population growth, or we may get there and then resource limitations might bring us back down. But there is some good news here, okay? Though the population is still growing, more people are being born than are dying, it has at least started to grow at a slower rate. So we are starting to flatten out a little bit, a sign that we're maybe approaching that carrying capacity and a sign that we're kind of slowing down to maybe a more sustainable rate of growth. But just to drive this home, take a look at this graph, okay? So what you have here on the x-axis is time. On the y-axis, you have population. So this goes back to 10,000 BCE when the population of the entire Earth was 4 million, okay? 4 million with an M, 10,000 years ago. Go forward 4,000 years, basically no change. You can hardly see it. Go forth another 4,000 years to 2000 BC. It's gone up a bit, but not much. Let's go to the year zero. So in 10,000 years, from 10,000 BC to the year zero, we got 190 million people. So we had 186 million people added. Then we go like this for a long, long time. And finally, in the year 1860, we hit a billion for the first time. Remember, a billion is 1,000 million. Okay. So think about that for a second. When did humans first appear? A couple 100,000 years ago. So a couple 100,000 years ago, up until the year 1860, so about 150 years ago, that's how long it took. It took a couple 100,000 years to get to our first billion people. Do you remember where we are now? Just 150 years later, we are at almost 8 billion people. So it took us a couple 100,000 years to get to our first billion, and then the next 7 billion only took 150 years. Exponential growth. Not only was it was growing faster and faster and faster. So notice 1.65 billion in 1900, only 100 years ago. 2 billion people in 1928. 3 billion in 1960. We're getting into the years now where some of your parents or maybe grandparents were being born. Okay. 4 billion in 1975. So the population has doubled since 1975, which is only like 40 years ago, right? And the population of the Earth has doubled. It took a couple 100,000 years to hit 4 billion, and then it took only 40 years to double that. Isn't that mind-blowing? Right? 5 billion in 1987, 6 billion in 1999. We only just hit 7 billion in 2011. And then this data is up to 2019, and we've already almost hit 8 billion. So think about that, right? It took a couple 100,000 years to hit 1 billion the first time. And then to add our last billion, it only took 8 years. Pretty incredible, the rate of growth here in humans, right? This is why it's not sustainable. We can't keep this rate of growth up. We will simply not have enough resources to support everyone. Now, like I said, the birth rate has gone down a little bit, that it's a bit closer to the death rate. So population growth is starting to flatten out. It's showing the beginnings of becoming an S curve instead of a J curve. Okay, if we're looking to live sustainably, we should probably be looking to keep that flattening of the curve going. Okay, so we've looked at limiting factors. We're going to look now a little bit more at two types of limiting factors. Okay, and we can split them up into density dependent and density independent factors. What is a density dependent factor? Well, that's just a factor that affects larger populations more frequently or more seriously than it will affect smaller populations, right? So in other words, the bigger your population is, the more you have to worry about this. Or it limits your population because of how big your population is. So become more significant as the population grows or as suitable habitat shrinks, right? Because it's density, it's how many organisms per square foot or whatever. So some examples of this: disease. If you're all packed in very tightly, disease spreads quickly, okay? Parasites and predation kind of go in the same category. If you're very tightly packed, predators start to know, okay, this is a good place to go hunt, I don't know, geese, right? So they go there and they start to limit the goose population because word got out that there was way too many geese here. Water access. If there's too many organisms in one ecosystem all drinking from the same water, well, there's only so much water, and eventually there's not enough for everybody, right? Same goes for food. Same exact idea. Oxygen availability. We saw that in the algal bloom, right? When the decomposers started breaking down the dead algae, they were way above their carrying capacity. And so eventually the ecosystem kind of had to collapse and reset because they had gone past a sustainable level. Sunlight, right? Plants do compete for sunlight, like we saw with those big tall trees that kind of smother out these smaller shrubs and stuff below them. Space. If there's just not enough room, there's not enough room. Goes for hunting, goes for food, goes for just finding a place to live, goes for grazing, all that stuff, okay? And introduced species. So an invasive species in a in a very dense population, well, they'll have a big impact right away. The other type is density independent, right? So again, dependent means it depends on that. So density dependent, it depends on how densely an area is populated. It will be worse if it's more densely populated. Density independent means it doesn't depend on it, right? So no matter what, no matter how densely populated this area is, these factors will limit the population there. So that's things like climate, right? Doesn't matter how many plants there are in a forest, when the winter comes and freezes everything, it's all going to die, right? Whether there were two shrubs or a complex ecosystem full of thousands of trees and bushes and grasses and everything, right? The climate limits how many things can live there. And then there's things like natural disasters, floods, fires, earthquakes, volcanic eruptions, meteor impacts. If a fire goes through an ecosystem, doesn't matter if it was a desert ecosystem or a rainforest ecosystem. Either way, the population that can live there is now limited by that fire once it goes through. So when we combine those, when we think of them both at once, the density dependent and the density independent limiting factors in a given area, we call it its environmental resistance. So if there's tons of food, tons of water, they never really have fires, there's always lots of rain, it's nice and sunny, that place has a very low environmental resistance. Think of environmental resistance like how much it resists population growth and life kind of taking off, right? If there's barely any food, barely any water, there's never rain, and a whole bunch of parasites, that has a very high environmental resistance. There's a lot of things limiting your population. You will have a very hard time growing your population there. It's very resistant to life blowing up there, right? Okay, so I like this graph. It's just a way to visualize it. So you can see we have some kind of fish here. Their population is growing. At first, it looks kind of like exponential growth, but then limiting factors start to come into play, right? And it hits what we call the carrying capacity. And then things start to say, okay, that's good. You can't grow anymore. And their population is limited. So you can see things like decreasing oxygen supply, right? More fish breathing more oxygen. There's only so much oxygen. Eventually, fish babies are going to start to die off because, well, there's just not enough oxygen. That helps keep the population in check. Lower food supply, right? Competition for food. So if there's not enough worms to go around and insects, right? Well, some fish are going to start dying out. And it's not like their population is going to, right? It's just going to sit at this more stable level. Disease, it spreads more quickly if there's fish all crowded around. Predators, as we've seen, when a prey population goes up, so does the predator population, right? Because there's more food for those predators now. So their population goes up, and then that starts to keep this population a little more in check. And in vice versa, their population keeps the predator population in check. Okay, and just also limited space. Okay, so I really like this graph for visualizing the idea of limiting factors keeping a population at roughly its carrying capacity. Of course, there will always be little fluctuations, but for the most part, with no disturbances, it should stay at a relatively stable level. So these things that we talked about here, what did this do? Well, it kind of took out the natural limiting factors that would have kept our population a little bit more in check, right? Things like disease, competition for resources. If you can grow your own food, you don't have to compete as much to get food. And so these kind of, in a way, brought us outside of the usual checks and balances of nature and allowed our population to start growing like crazy. Okay, and back to these. So what is biotic potential? What are J curves and S curves? What do they show? What is the carrying capacity? What are density dependent and density independent limiting factors? What is meant by an ecosystem's environmental resistance? And how does the human population's growth rate compare to other species' growth rates?